Welcome back, engineers. We are discussing common techniques and algorithms in system design and high-level design. And in this video, let's talk about Bloom filters. I hope you're ready. Let's get started. So Bloom filters is a very commonly used technique and there are a lot of applications for it. Let's try to understand what is the problem that it is trying to solve and then we'll see how it actually works, right? So let's say we are searching for the word APBLE in the English dictionary. It's misspelled by purpose to demonstrate how Bloom filters actually make sense and where it makes sense. So let's say we are searching for APBLE in the English dictionary, right? So English dictionary, let's say, is having about 1 million words. And let's say we have a server set up like this. Let's say we have a client, a server, and at the back end we have a database. And because there are so many words, we thought we will distribute it across different shards, and each shard will have different set of words from the English dictionary. So let's say shard 0 has all the words starting with alphabet A all the way up to alphabet G. And shard 1 has H to M, shard 2 has N to S, shard 3 has T to Z, right? So let's say this is our database setup, right? So how does this search actually work? So let's say we are giving a request from client to server, look for this word and tell me the definition. And now what the server does is, because it is having multiple shards, it needs to know where to look for this word and find the definition. So for that, it will use some kind of a hash function and sends the key APBLE to this hash function and gets some kind of an integer which will identify a particular server where the data lies, right? Let's say this hash function has returned the number 0 and we know that APBLE is possible to be in the shard 0. So we make a request to the shard and we are expecting a response, right? So this is a database call. Let's say we have a table like this, which is the English dictionary table. It has the words in one column and definitions in the other column. And let's say we don't have any indexing at this point. So we are going to look for all the words in this word dictionary until we find this, but we won't be able to find it because it is a misspelled word anyway. So our operation is turning out to be expensive, which is linear time of an operation, right? So let's say there was a smart engineer in the team and they have designed an index for this table. Let's say we have an index which is for the column word, and let's say this is now a sorted list of words, right? Let's say this whole thing is sorted. So with this sorted index, we can now perform binary search, which is bringing down the time complexity to O of log n. So even with this, we have performed O of log n operation and we haven't found any APBLE in the dictionary and we return with empty. Right? So if you think about this whole cycle, right? Client to server, there is one request, server to this hash function to shard for the connection request, and then connection to the actual table. Maybe we already have an index to the actual index, and then we are doing a RAM check with the index, or we are doing the list check on the direct table, whatever may be the case. So we are doing all these operations and then we are returning. And since this is a distributed system, there are obviously network latencies and network calls also involved, right? So this whole cycle is a large operation. And imagine if it were not a sharded database and it was one single database with billion entries. To search through such a big space of strings just to find another string would be a very computative operation, right? So this is the problem that Bloom filters are solving, right? So let's say we have a Bloom filter in place instead of whole this setup. And let's see how quickly we can do this. So let's say we have a client and server setup like this. So client is there, server is there, and we have the entire backend similar to what we had before. But instead of doing a hash call, we now have a Bloom filter in the server side, which will take care of minimizing our time complexity, right? So let's say we already have built a Bloom filter with all the words in the English dictionary, and this now can be used as a filter. So what we'll do is we'll apply the Bloom filter to the same word APBLE, and it returns a firm no, right? It has confirmed to us that there is no such word in the English dictionary. So we can immediately return from here. We don't have to do any network call to the database or to the index, do any disk lookup, RAM lookup, and nothing like that. We can just rely on the memory of the server itself. This Bloom filter generally resides on the RAM. So it is quick, it is efficient, and we can give out the answer immediately. Right? So this is one of the use cases where we want to do quick lookup, right? We want to check if some string is existing among millions and billions of strings, right? So this lookup is actually O of k operation depending on the number of hash functions we use. So we'll take a look at how Bloom filter works and what is the time complexity and efficiency of this. But for now, just remember that if we have to search for one particular string among a billion strings, Bloom filters are your best choice. right? Now let's see what are the other applications in which Bloom filters can be used, right? So wherever you need membership testing and you want to understand whether a member exists in a set or not, right? That's where you can use Bloom filters. For example, web crawlers. So you're using a web crawler, you started at some website and you're crawling through the pages of particular website. So you go page by page, one page can have inner links which will navigate to some other pages and you're crawling through all those pages, and it is possible that some pages you have already visited. So how do we keep track of the pages being visited among billions of websites, right? So in that case, we can make use of Bloom filters for quick and efficient check. Just a quick lookup to see whether a site has been visited or not. We can use Bloom filters there. So this can also be used in CDNs, content delivery networks, where people request the same assets multiple times. So we can use Bloom filters here to see if that asset has been visited before. We can also use this in browser caching to only cache those sites that have been visited by the user, right? And we can also use this in databases, which we have seen just now as an example. We can use this in spam filtering, whether we want to analyze if one particular email address is part of any denied list or not. So let's say we have a specific database where we are keeping track of all these spam email addresses. So we can make use of this there. We can do spell checkers. This is also an example of what we have seen before. Next is network packet filtering. When you're analyzing network packets, maybe there are some malicious URLs that you're suspecting. So you can do Bloom filters there to do some URL scanning and so on, right? So there can be many more applications like this, but all you need to remember is you're doing membership testing here. So you have a set of strings, you're testing one string against this string to see if the string exists in that set or not, right? That's all there is to know about Bloom filters. Now let's see what is a Bloom filter and how it works, right? It sounds complex, but it is actually quite simple. The data structure is quite easy to implement and simple to understand. So let's see. So what is a Bloom filter? Bloom filter, as you can see here, is a simple bit array. So what is a bit array? Every element in this array is either a 0 or a 1, right? So that is why it is called a bit array. So we are only visited in storing 0 and 1. 0 means not visited and 1 means visited, right? That's all we need to know about the data structure. It is an array. It can be of small size, large size, depending on the corpus of strings that you're using or the use case that you have. And all we are storing are zeros and ones, right? Now let's see how it actually works. So how does the Bloom filter work? Let me close this. So let's say we have a bit array and everything is initialized to 0. So all the numbers in the bit array are initially 0. So let's say we want to add the word cat into this bit array. So how do we do that? So we will have hash functions. So there can be multiple hash functions like this. For simpler understanding, let's take two hash functions. The first hash function will take in the word cat and it will break down the word into characters CAT, and it will do a sum of ASCII codes, right? And then we will do a modulo 10. Let's say this hash function is giving out the number 2. So what do? We go here and change the value from 0 to 1 for the index 2. That's it. So we have activated this particular position, let's say. And similarly, there is a second hash function. Let's say this is just taking the length of string and doing a modulo of 10, right? So there can be complex hash functions like this or simple ones depending on the use case, but it is returning some integer which will be an index on the bit array, right? So let's say this is returning the number 3. So we will go ahead and activate 3. So what this tells is cat is now added to the bit array. Now similarly, let's try to add the word dog. For dog, hash function 1 will return the number 4, hash function 2 will return the number 3, right? So let's say we have already activated 3. Now let's activate the index 4. So we'll erase this and we will simply add the number 1 here. Now we have added 2 words into our Bloom filter, right? Let's say this is our set. Our set has 2 words, cat and dog. Now let's try to search for the word bat in this, right? So bat, since it is not there, we are expecting that the Bloom filter will give out the response like this. So let's say we are passing the same bat into the same hash functions h1 and h2, and it is returning 1, 3 as the output. So we will check here. What is at index 1? We have a 0 here. And what is at index 3? We have a 1 here. So since one of the inputs is still a 0, the Bloom filter will return a firm no. Okay, Bloom filter is confident that the word bat is not there in the set which is containing cat and dog, right? Now let's take a look at the word eat. So if you pass the word eat into these hash functions, we will get the numbers 4, 3, right? So we'll go to the bit array and see index 4, index 3. So we are getting 1, 1 here. So in this case, the Bloom filter will return a maybe yes. Maybe yes. So Bloom filter is never sure if a particular string is definitely present in the bit array. It is only a probabilistic approach to check if something is available in the set or not, right? So in our case, we have eat here, which is giving out 4, 3, and in the bit array we got 1, 1. So you must be thinking, since it is 1, 1, it is a definite yes. But this 1, 1 is not created by the word eat. It has been created by a combination of these two, or rather dog in this case, right? Because dog also got 4, 3, we have activated 3, 4 based on dog, not based on the word eat, right? That's why it is a maybe yes. So that is one thing to remember about Bloom filter, that it can give false positive. This is a case of false positive. So what will be a true positive? Let's say if I'm searching for dog again, dog will give out the hash function results are 4, 3, and in the bit array we'll get 1, 1, and even then it will give out a response as maybe yes, but we know that dog is part of the set, so it is a true positive. But when in the case of E, it is a false positive. So that is one thing to remember, that Bloom filter gives out false positives, but it will never give out false negatives, right? In this case, this was a true negative. The word bat is not part of the set and it is giving out a firm no, right? Which is correct. But it will never give out a false negative. So two things to remember: Bloom filter will never give false negative, but it is possible that it will give false positive. So that is why it is a probabilistic data structure, right? So how do we use this now? So when it is giving out a maybe yes, we can do an additional check, right? So in a case of our dictionary example, we were searching for APPLE and the Bloom filter given as a firm no. So we know that we can directly return from there. But if we have given the right keyword, APPLE, which is apple, so it will give out a maybe yes. Then we are sure that maybe this word is part of the dictionary. That is when we initiate the network calls. We will do the lookups on the database table or the index or whatever optimization we have going on there, right? So this will save us a lot of time because we are able to eliminate true negatives in the first step itself, right? That is why Bloom filters are very effective. Now let's see the time complexity of insert and search. Give it a second, pause the video and think about what can be the time complexity for insert and search, right? I'll give you a few seconds. Okay, now let's see. For insert, what did we do? We had an array initialized already. We didn't need to do anything there. And when we got a new word called cat, we sent it across all the hash functions that we have. Let's say we have k hash functions like this. So we were triggering k operations, right? And once we have the number output for this, we got 2, 3, right? Activating the bit array is just a constant operation, right? So we have O of k for the number of hash functions, and then we have O of 1 for actually updating the array, right? So our insert operation is O of k. And what will be for the search? It is exactly the same, because let's say we were searching for the word eat, we were also passing the word eat for all these hash functions, and we were getting out the indexes to look into the bit array, right? So again, we were doing O of k, and for searching into the bit array, we are doing a constant operation, because lookup using index in an array is a constant operation. So overall it is O of k, right? So we have reduced the time complexity from O of n, O of log n to simple O of k, which is the number of hash functions that we have, right? So that is the advantage of Bloom filters. Now let's see how we can reduce the false positives. So in our example, we took a small bit array of size 10, but in the real scenarios, the size of the Bloom filter array can be quite large, and the larger the array, the less are the chances for having false positives, right? So increase the size of the bit array and also use more complex and increase the number of hash functions if you want to reduce the false positives, right? These are a couple of ways to do that. Now let's see the pros and cons of Bloom filters. We are getting very good performance because we have reduced the time complexity to a great extent, and we are avoiding unnecessary lookups on the DB side for disk or RAM lookups, right? And it is also memory efficient because we are simply storing a bit array, and there are no false negatives, which we have seen just before. It will always give out a firm no when the string is not present in the set, right? And the cons are it will give out false positives, so we need to do some additional check just to be sure. And there is no deletion support, right? So let's say we want to delete the word dog from the set. We cannot do that because the index is 4, 3, even though they were activated here in the bit array, these were not activated by just the word dog, right? So you can see here that the number 3 was activated actually by cat, right? So it will create a conflict. So deletion support is not there in Bloom filters. So it remembers everything once it is set. And finally, it requires a bit of fine tuning to get to the optimal probability of dealing with false positives and false negatives. But once we have that, Bloom filters are a fantastic option when you have an application or a use case that we have discussed before, right? So this is all we need to know about Bloom filters, guys. Thank you so much for watching. If you have any doubts, definitely let me know. Please leave a like if you found this helpful. Please subscribe if you haven't done already. I will see you in the next one. Cheers.